Yeah, thanks everyone. I'm Matthias, as René has introduced me. I've taken part together with my colleague David Fischer, who cannot be here today, he is on vacation, in a little Retrieval Augmented Generation challenge in spring of this year, and will summarize our findings here. The challenge happened in connection with SIGIR. SIGIR, for those who might not be in academia anymore, is the special interest group for information retrieval of the ACM, the Association of Computing Machinery. Exists since 1963 and holds an annual academic conference since the 70s. Maybe a bit similar to Haystack, but a lot bigger. So it was went on for a full week, had more than 500 accepted papers. I didn't check how many submissions they had. It's, as you might know, a huge thing in the academic world. And this year they organized a little challenge or competition and asked teams to participate. And they called it the LiveRAG challenge. If you're familiar with competitions, they usually involve some kind of a task. You get a data set, and then you have a few weeks to submit your solution to the task, your kind of results, and you're ongoingly evaluated and published on a leaderboard, and teams compete. This was a bit different. It was supposed to be more live. So some parts of the data set were only revealed during the competition time or on the challenge day, and the teams only had a limited amount of time to submit their results. As part of our application, so we like challenges, so we applied. As part of the application, we needed to come up with a name because they wanted to have anonymous applications. We came up with Ragmatas, which was kind of one of the last few puns involving RAG that wasn't already taken. And to our surprise, we got accepted. The challenge task was then announced, and it was to generate answers to 500 questions grounded in a given corpus within 2 hours' time. So that was a bit less live than anticipated. There was no instant sub-second answering being required. If you do the math, we had about 14 seconds per question. And they also had put no real constraint on the parallelism or the hardware we were allowed to use. But we said, okay, let's still try to explore how far we can get while keeping things simple. We decided that we want to solve the challenge running as much as possible on our local notebooks, which is a first generation M1 here. And we also had a ThinkPad P17 with a NVIDIA GPU. The corpus that we were supposed to use was FineWeb 10BT. I have some slides on the data later on. The generation model for generating the answers was fixed to be Falcon 3 10B. You were allowed to use other LLMs in your retrieval as long as they had less or up to 10 billion parameters. Yeah, and I think some teams used the help of other LLMs, so there was a lot of freedom in how you could solve the challenge. The question that we were getting were generated using a tool called Data Morgana. That was something that people involved with the organization of the challenge had developed. And the answers were in the end judged by a larger LLM for correctness and faithfulness with human re-evaluation. Some notes about the timeline, maybe a bit hard to read. We got accepted on the 12th of March, got access to this Data Morgana tool to generate our test data set on the 20th, and then had about 6-7 weeks of time for this little side project. So kind of our time to experiment. Some words about the corpus. It's, I don't know, is anyone familiar with FineWeb? Anyone working with web data? Roman is? Okay. So FineWeb calls itself as the finest collection of data the web has to offer. It's a huge data set based on the content of Common Crawl. So Common Crawl, the project probably more widely known, that's crawling the internet for, I think, a lot more than a decade now, and is publishing their dumps. And the data is then post-processed. The dataset has been released by the Hugging Face people. One thing they do with the Common Crawl data is that they use a superior way to extract the actual text. So if you imagine web pages, one of the challenges is to extract the relevant content from a page. You want to avoid having all the boilerplate navigation elements in the extracted text, etc. So they use a state-of-the-art library called Traffilatura for this. The other aspect of fine web is that the documents are filtered. So they take the Common Crawl dumps and filter them based on a lot of heuristics. For example, bad domains are excluded, domains that, or URLs that contain certain words are excluded. But there's, I think, very little in-document filtering. So if you want to, an even finer web, you would have to do this post-processing yourself. The fine web dataset itself they publish sampled data of fine web, and one of these samples is called FineWeb 10BT that we were supposed to use. It contained 14.86 million documents, almost all in English, and it's called FineWeb 10BT because in aggregate that's about 10 billion BERT tokens. And yeah, it's web data. So if you have a look at it, it's really random stuff from around the internet. You can have things like this, a random article about, I think, a fish bowl, probably made from some e-commerce oriented website. It can be a lengthy article, probably from some blog around, I don't know, college-style hockey or something, very specific, hard to interpret without any further context. But also some, I just randomly sampled documents. So it's one that is just giving a definition of what a Supreme Court usually is in a country. If you look at the data from a kind of token count perspective, fine web data has a mean length of around 680 tokens per document, with a median of around 400. It's a bit hard to see following this kind of relatively, let's say, normal bell-shaped distribution. And it's quite similar to how the distribution looks for the English Wikipedia, where the mean length is approximately the same, of it's 670 tokens, and the median is a bit lower at 300. It's, these numbers are important to keep in mind when you look at what embedding model should I use to actually embed this data if you want to use semantic search. Some words about the tool to generate the synthetic questions. So they called it Data Morgana. It's an LLM prompting tool to generate relevance data sets, and was used to generate the data set for this challenge. It's provided documents from a corpus. So here they configured the FineWeb corpus, and it's usually given the task, or it's usually supplied with 1 or 2 documents, and then given the task to generate useful questions based on these 1 or 2 documents. And these questions can have different properties, and you can configure which properties you want and what kind of distribution represented in your data set. And these properties can then be, for example, the degree of familiarity of a user with the data. So is your end user expert or novice? Is the question formulated in a long or a concise way? Is it a short one? Is it more factoid, or is it more open-ended? Does it contain any errors, spelling mistakes, for example? And the output is the configuration that was actually then used to generate these, for each question, the documents and the question, of course, and the expected answer. The generation model Falcon 3 10B comes from the Technology Innovation Institute in Abu Dhabi, was released in December 24, and is one of the best models in its class, so in the 7B, 10B class. It actually comes with a license derived from the Apache license, so pretty similar. Don't really know the exact differences, but it's a relatively open model, let's put it like this. I hadn't heard about it beforehand, or before the competition. I think that its release was a bit overshadowed by the whole DeepSeek releases that also happened in December and January. But in this challenge, I think the model did quite well for us and the other participants. So we can recommend it. You can download it, but we also were provided with API access. Okay, that were the constraints. Now, the first thing you have to think about when you build a system is how you evaluate it. Fortunately, for a retrieval augmented generation system, we can use what's already out there. So we have a retrieval step that turns the question into, or retrieves the relevant documents for a question, and then we have a generation step where we use these documents to generate an answer. And for the retrieval step, we would compare the retrieved documents to the golden document usually, and use metrics like recall precision or MRR to judge how good our retrieval is. For the generation step, we have the now well-known metrics like correctness, comparing the answer to the gold answer, or faithfulness, where we have a look at how much our answer is grounded in the provided documents from the prompt. So we use Data Morgana to create these kind of golden data sets. And I think we had something around 1,000 questions in our evaluation set. For retrieval, we went on and started simple with a basic pipeline. So the main idea was that we have some initial retrieval where we really fetch a lot of documents. We take fetch the initial candidates and have subsequent steps where we try to push the relevant documents from this larger set into ever smaller top N results. The metric we applied was recall at N. So recall had the nice intuition that you can actually understand it as the percentage of relevant documents we have captured in our top N results. So we started with a recall at 1,000 for the initial retriever, then had a look at ever smaller N's, recall at 100 after the initial step, up to a recall at 5 for the final step, because we had the initial goal of using 5 documents in our generation prompt. For the initial retrieval, we started with a BM25 retriever. I think we started with OpenSearch, then said, we don't really need a server running all the time. Let's just use a library, discovered BM25S, which worked well, and then just use that. By the way, that produced exactly the same scores as OpenSearch, so why not just use a library to keep it simple? And we also stayed with the relatively standard processing with just an English stem and a stop word filter. For semantic, of course, there was a lot more work to do. First of all, you have to select an embedding model. We just went to the massive text embedding benchmark leaderboard, the MTab leaderboard, sorted the models by retrieval performance, and then had a look at what models could provide us with a good trade-off of retrieval quality and inference time. So we were looking at models that had way less than 1 billion parameters, and tried out a few and had a look at if we could get them running on our local machines and at an acceptable inference time. So these are in addition, to BM25, we tried 3 more models, or we tried many more, but I think we only ran the full data set for three models. And as you can see, the keyword retriever BM25 worked well for some queries, most likely for the ones where there was an exact keyword match for very discriminative terms. The comparison between the semantic retrievers, bit of a caveat here, is a bit unfair because the 2 models above have a context window of only 512 tokens, while the lower one goes up to 8,000 tokens, and we didn't chunk in our initial evaluation. So they were a bit at a disadvantage, and we had to decide, do we try this again with chunking and overlap? And then we decided, oh no, Snowflake Arctic Embed is the one. Let's go with that one, and don't re-evaluate with chunking, because chunking would have meant that we turn our 15 million documents into about 30 million chunks, and we didn't want to go that overhead. And as you might remember from distribution of the token length, there was a kind of a mean at around 600 or so. So we were well in the so there was only a very small proportion of documents that were longer than 8,000 tokens. So inference time, I already mentioned it, is a challenge. So technically, that's the biggest challenge if you do a retrieval project involving semantic search. If you look at the time it takes to generate embeddings on our local machines, it ranges from, if you take the BGE base EN model, that on my ThinkPad would have taken 12 hours to embed the whole corpus, still reasonable, up to the Snowflake one, that would have taken 171 days on my MacBook in full precision, or 206 hours on the ThinkPad. So that's where we said, okay, as part of the challenge, we were also supplied with some AWS credits. Now was the time to use them. So we actually created a little distributed embedding system to create these embeddings in just a few hours on spot instances. And the next, maybe unexpected challenge was actually getting it indexed. So we had now about 15 million 1024 dimensional vectors. Try to squeeze them into OpenSearch without kind of further pre-processing. With Lucene, just was really slow with the Lucene backend. It got slower and slower over time, probably due to segment merges. With the FICE backend, it just stopped after 1.5 million documents without continuing. Similar issue with Quadrant, where we didn't get it running. And fortunately, we found the USearch library, again, a library that then just worked. So that was kind of our savior in this moment. And so far, we have talked about querying using the original question. And we already saw that, for some questions, we couldn't get good results, even at the best in the top 1,000. So we added another search pass using a hypothetical generated paragraph. So we used DLM, we used Falcon 310B to generate a hypothetical answer paragraph and had another search pass using that. The challenge with that approach is that you have to create a paragraph that's sufficiently different from the terms in your question. Otherwise, the BM25 retriever will just find the same things using kind of a slightly different phrasing of the same thing. So that's kind of another initial retriever we added. Then we had our 4 retrievers, so the semantic one, the keyword one, searching for the original question, and the hypothetical answer paragraph, and then we had to combine the results. We tried some score-based combination. It didn't really work, so we went back to reciprocal rank fusion, did a grid search, so we tried all combinations of results here with any hyperparameter for RF of k between 1 and 100, and we came up with that, or grid search found that it makes sense to actually use all of the 4 retrievers, and the K value I think we used was 79 or so. And that improved our recall at 100 from 0.71 to 0.81. Next, the re-ranker step. So goal for the re-ranker was to bring our 1,100 results now to a good recall at 20. So we wanted to squeeze the good documents that we knew that were in the top 100 into the top 20, ideally. Searching for good re-ranker I found a bit difficult. There is no, I wasn't really aware of a good leaderboard. So we just sampled some literature and we just went with, I think we compared a Colbert re-ranker and this in-ranker, relatively small one, 200 million parameters, and applied that to the results. In this case, we actually then did the chunking. So for our 100 documents, we did some live chunking during re-ranking. And that gave us a modest improvement of the recall at 20 that went from 0.65 to 0.7. And finally, we thought, okay, now we have or in 70% of the cases, roughly, we have the good results in the top 20. Now let's filter out the irrelevant ones. And then we get the good results in the top 5. And we use a heavyweight LLM-based relevance filter. So we actually ask an LLM, our Falcon LLM again, to say whether a document is relevant or not, and then just remove the irrelevant ones. That turned out not to work. So we tried different prompts, a more strict prompt, a more lenient prompt. And in the end, our strict prompt produced too many false negatives. So it was actually removing from the results where we already had a good document in the top 5. It occasionally found them to be irrelevant. And in the more lenient prompt, it had too many false positives. So it didn't really remove much of the irrelevant ones. So in the end, that was kind of, it didn't make things worse, but also didn't improve the overall results. So quick summary of retrieval. So this graph shows kind of the incremental recall improvements over the different steps. On the y-axis, there's the recall at position K from 0 to 1. And the horizontal lines are the different positions. So I think what I just showed is the best initial retriever was Arctic Embed, where we moved from this position in the fused one to this position. So from 0.71 to 0.81. And in the re-ranker case, we went from this to this on position 20. So from 0.65 to 0.7. And our LLM filter here on the right kept things the same. It removed some of the relevant documents, but also some of the irrelevant ones. So it was, in the end, we didn't use it because it didn't really improve the situation and it cost time, of course. So we had our documents, so we were ready for the generation step. We just used a basic prompt, asked for or we just used the documents as they were and truncated them after 8,000 characters in the first round. We requested a document reference, so we asked the LLM to provide some kind of a citation of where it has found that fact or where it is grounding the answer on. So that was our thought of increasing the chance to getting an answer actually derived from the documents. We also provided a fallback answer that the LLM could use if it cannot answer the question based on the given documents, so that we could detect that it failed. And in the end, we were in a position where we knew our recall at 5, it was only 0.52. So in about 50% of the cases, there was some chance that we had only irrelevant documents in our top 5 results. So we implemented a multi-round approach. We fixed the character window to 40,000 characters, but then tried with an increasing number of documents. So we started with 5 documents and 8,000 characters, then with 10 documents and 4,000 characters, and so on, until we even fed in the first 30, but only the first 1,365 characters. Okay, the results. So the actual challenge happened in 2 batches, a morning one and an afternoon one. We ended up at position 5 in the second batch. Overall, we were at 6th. And the organizers did some human evaluation, re-evaluation, and put us at position 8 in the end, which wasn't a bad outcome from 25 teams, we thought. We were, of course, a bit disappointed that our LM precision filter did not really work in the end, but we were, I think, pleased that our relatively basic approach got us that far. Of course, then afterwards you think about, oh, what could we have done differently? So if you look at the competition winners, some were just throwing more compute at the problem. So that kind of is always can be a simple solution. So you can use a more powerful re-ranker. Ours was still relatively smallish. I think some even used 1,000 documents in the re-ranking process. So we only went to the top 100. And that probably would have given us some extra points that we missed. It's relatively easy to do, but for us it would have probably required to run this in the cloud, or at least with a higher parallelism than just one notebook. Then I think what we could have done is also more human evaluation, or eyeballing, as Stavros called it. So we never really looked deeply at the underperforming queries. And we had queries where the right document was not even in the top 1,000. So what's really happening there? So that's something I think in a real project, where it's not a side project you do for a couple of weeks with just looking at numbers, you would actually spend some time in looking at these queries and do some kind of put your brain at work and think about what's going on there. Which is also, I think, would raise the question: how good is our relevance data set? Is the idea that this question set that is generated from just a few documents is a good proxy of the overall retrieval quality, or could there be thousands of other relevant documents for the same question that might be even better, and how can we generate a data set for them? Then I think what we also didn't really do is, or could have done, is the be more specific on to react on specific query categories. So as you remember, there were different categories put into the Data Morgana tool, and I think it would have been possible to actually detect what kind of query we're facing and then react with a different retrieval pipeline. For example, do another round of search with an expansion that goes beyond the height approach we took for very short queries, or even do spelling correction or something like that when we detect a spelling mistake, and do a spelling corrected BM25 pass. Then we also didn't spend that much time on prompt improvements, so we just threw 40,000 characters from the truncated documents into the prompt. And our different retrieval steps were tightly separated, or strictly separated, and we could have used the scores from the previous re-ranker step to stitch together kind of more of the hot parts of the document, because they were already kind of known by the re-ranker. Or we could have just evaluated this 40K threshold more thoroughly. Then chunking, yeah, we didn't do it. Maybe would have helped. I don't know. And finally, I think the biggest effort would have been if we had actually tried to kind of do some more content cleansing or content preparation. So you could imagine if you're facing a data set of 15 million documents, there is a way to get them more tightly or get them into a better shape than they still come out of the fine web heuristics. And there are some papers out there that kind of even work on a finer web than fine web. Okay, my takeaways would be, yeah, competitions are a fun way to learn here, especially if they combine some kind of quality goal with technical constraints. So you have some of a level playing field with your competitors. So if it's you can spend the time, it's worth the effort. And yeah, so I'm bad at doing online courses and tutorials. So a challenge gives you a lot more focus. You learn things much more quickly. So for example, how to get the NVIDIA CUDA stack running on Windows, which I've never done before. How to fine-tune an embedding model, something that we also tried earlier on, or something like how to create a distributed embedding service on AWS Spot instances. Some of these kind of little side projects during the side project, I guess, were the parts that were the most fun and where we had the most kind of learnings from. I think the second one is that, yeah, keeping it simple and getting the basics right is always kind of a good start. Gets you to a decent, can get you to a decent RAG system, and anything that goes beyond decent, requires, yeah, incrementally more effort, and you have some kind of further improvements with diminishing returns. So that's, I think, my takeaway. If you want to look at what the others did, especially the ones maybe that won the competition, there's a public reports page on Hugging Face that contains more data, and all the teams have published their papers. So yeah, feel free to look into it. Okay, thank you.
Do we have any questions to Matthias? I go there first.
Did you look what the team number 1 from China or other top winners did? Like anything to learn from the top winners?
So I think there was, my summary would be there were two aspects. One is really have more compute and, as I said, use a larger re-ranking model or re-rank more documents. So I think the approaches were not that earth-shaking. Yeah? So it was something you would expect. Some spent more time in evaluating the actual generation prompts and techniques. So from instruct RAG to, I don't remember the exact names of them, but you can do a lot more in the generation prompt, asking it to more grounding, reasoning, do another step to see how well it did the first step. So this kind of multi-step generation. But I don't think there was any huge kind of ground-shaking new stuff. I think some tried agentic stuff, and there were, I think some of them also scored relatively high, but it wasn't that there was 7 teams used a complex agent system to solve the challenge. That wasn't the case.
Hey, thanks for the talk. I have a question. Did you struggle at some points with the time budget that you had? You mentioned like 14 seconds for an answer. If so, where was like the hot spots? If not, what would you do more with the time that you were given?
No, I think, yeah, you can really parallelize this heavily. Yeah, so you don't run this question by question in the U-search case. You run them. I don't know how many we ran in parallel, but on one machine. I think the most time was spent during the re-ranker, because that really had to, you had to get all the chunks into it, and so that was kind of the most compute-heavy part for relatively little gain, I would say. I think the search was probably done in a few minutes. So.
Okay. Another time-related question, but this time about your time, from the online audience. Where did you spend the most of your thinking time in this challenge?
That's a good question, because we really started at 0. I think So we started slowly and very, say, experimentally. So we started with a small subset of the data set, something I would always recommend, as we didn't have access to the Data Morgana tool. So we tried to generate some of our own questions. We tried out a few data sets, a few embedding models. We tried to fine-tune an embedding model based on the output of the Data Morgana questions. I think, what did we spend the most time? I think in these competitions, it's also a bit kind of, you can choose. Yeah. So actually, I think I spent the most time of building this distributed embedder because that was the most fun of the project. So there is some kind of degree of freedom. I mean, if you absolutely want to win this competition, that's maybe different. Yeah. So we really had two focuses. We wanted to test this LLM-based precision filter that didn't really work out, and yeah, have some fun on the side.
All right. Go there first.
I'm wondering, with the models that have, for example, bigger context windows, how do you choose basically how much context you're giving the model and letting it choose from that context, or how you restrain how much information you're giving it, and basically you're choosing the context you're giving it?
So for the so we just truncated. So we just gave it the first 8,000 tokens of the document, and in the case where we have chosen one of the other embedding models with lower dimensions, with also shorter context window, I think we would have just chunked with overlap and also given it the whole chunk. So there was no sub-selection of documents. We just truncated after 8,000 tokens. And as I showed on the FineWeb dataset properties, there were very few documents longer than 8,000 chunks. So I guess there was very little to lose by just truncating there.
Hey, so sorry if I missed it, but how were the original retrieval questions or queries generated? Was it always just the original question, or was there some kind of pre-processing step for those queries? And did you see any of the other competitors try like pre-processing those queries?
So we just used the question. I mean, they were stamped and stop-word filtered in the BM25 case, but we used the original question in the semantic case. The other competitors did a lot, or some other competitors did a lot more there. They generated a lot more queries and ran multiple queries per question. So that's one of the things we could have done. And maybe that would also have solved our recall at 1,000 problem, where we wouldn't even have a good document in some cases. Yeah.
Thanks for sharing. You mentioned about how you could have done more with different pipelines for different categories of queries, I think. Could you unpack a little bit, maybe with some examples of what you meant by that? Yeah,
I think I only realized afterwards, eyeballing the questions again, that some had some, I don't remember the exact category, but somewhere using some kind of a slang language, something you could, I mean, it didn't seem even natural, but it's something that you could maybe detect using an LLM, say, okay, if this is in this category, then we really have to reverse this kind of slang encoder that somehow created this question. So that was kind of the thinking behind, oh yeah, we should really have tried to detect what categories they have created there, what kind of question categories, yeah.
Okay, thank you very much again, Matthias.
Thank you.